Hi everyone. Okay, so now I think everything is fine. Let's get started. So now we will discuss some other questions which have not been discussed in the previous session, which was taken with Deepak sir. Okay, so let's just get started. Okay, so I hope you can hear me. If there is any issue in audio or video, just let me know, or otherwise let's just start the session. So this is going to be the part two in the sense that we have already, seen the part one taken by Deepak sir. So let's just start this part two. Okay. Okay. So let's see this question. This question is from algorithms, and this question was easy. But the intention to give this question is to make sure that you know how to write the recursive equations. So see here that we are saying that silly sort. Okay, there is some silly sort that is being called. Okay. So just a second. Yeah. Yeah. So there is some silly sort that is being called, and then they are saying that they are calling it on ny2 element and ny2 element, and then they are doing some concatenation. I mean the result they are concatenating. Everything is defined here. That what is this concatenation? Assume that concatenation of two string take theta of n. Okay. Suppose this concatenation is taking theta of n time. Then they are asking which of the following is the correct recurrence relation. See here, you just go step by step. Suppose Tn is the time that is taken by this algorithm for the size n, right? Then for the size n by 2, since you are doing the same thing recursive, okay? So for the size n by 2, it will take Tn by 2 time. And then for this also it will take one more Tn by 2. So 2Tn by 2 plus whatever is time is taken for these two. So this will take order of n time, and this will take n log n time, because this is a merge sort, and merge sort is being done on the size of n. So that's why it will take order of n for the concatenation plus order of n log n for the merge sort. Okay. So you can see that for this particular question, actually these things are actually useless. I mean, anyway, we are doing the merge sort, so whatever you do earlier doesn't really matter. But it will anyway increase the time complexity. So the point here is to note is that you are having Tn by 2 for the recursive. Okay. See, you are having this Tn by 2. The main important part of this question is to write this one. Okay, the first part of the recurrence relation, which means you are able to figure out that okay, 2Tn by 2 will be for the recurrence, and for the remaining it will be just static, some n log n, something like this, right? So you can solve this recurrence, I mean, if you want to, but they are not asking you to solve the recurrence. So basically, this is n plus n log n, which is nothing but n log n. I mean, you can just represent this as theta of n log n. Okay, so 2Tn by 2 plus theta of n log n. So I think B is the correct answer here. And if you want, you can also solve this recurrence. That what you can do, you can apply the Master's theorem. So it is n s power log base b a and then n log n. Which one is larger? So you can say it is n and it is n log n. So n log n is larger, but it is not polynomially larger. So can you tell me what will the answer? Will the answer be n log n? Will the answer be n log n? The answer is no, right? Answer is no. So what will the answer? It will be something like this. See, n log n is greater, but it is log n times greater. If it is log n times greater, then n log n, whatever is the function into log n will be the answer, right? So which means n log n square, right? Is it greater than merge sort? Is it greater than merge sort? Obviously, it is greater than merge sort. Why? Because we are basically doing some unnecessary work, and then we are doing the merge sort. So the final answer was expected to be greater than merge sort, right? So n log n square is the final answer. Okay, but in the question they have not asked the time complexity. They have just asked for the recurrence relation. Actually, to be very honest, when I was making this question, at that time I thought that let me ask the time complexity directly. Okay, but then I thought that, okay, I don't know, maybe it will be too tough for you, because if we make, especially go classes, if we make little bit tough, you people think that we are making too tough. So that's why, like, I mean, obviously we will keep the gate level, but I thought that let's not ask for the time complexity, let's just ask for the recurrence relation. Okay, asking for the recurrence relation was, I think, easy for this question. Now let's just move to the next question. This question was related to Bellman Ford, and then what they are saying in this question is that, that this graph is given, and then distance to B, some array is given. Okay, it denotes the current shortest distance known from source vertex S to B, which means what is the current distance? It is basically saved in distance to B, some array. Okay, and then they are saying the algorithm follows this strictly this order. Okay, for the uh, strictly this order for the relaxation, right? So it is Bellman Ford algorithm, and it is following strictly this order. So let's just solve this question. It is easy question only. So initially this will be 0, and everything else will be infinity. Okay, this is the initial configuration, right? And then let's just relax in this order. So 0 to 1, if you relax this will be 80. Sorry, 0 to 1. So if you relax this will be 100. And then 0 to 3, this will be 80. And then 0 to 4, this will be 30. And then 1 to 2, then 1 to 2, it will be 110. Then 4 to 1, where is 4? 4 to 1. So it will be 30 plus 50, it will be 80. So it will get updated. Okay, because I'm getting the shorter distance. 4 to 2, 4 to 2 is this one. So this is 130, so it will not get updated. 4 to 3, this is 40. So 4 to 3, sorry, 4 to 3, so this will be 70. So it will get updated. So it will get updated to 70, right? So it will get updated to 70. Now 4 to 5, 4 to 5, it will get updated to, from infinity it will get updated to 40, right? And 5 to 2 is 5 to 2, right? Then 5 to 2, it is 40, and then 60, so it will get updated to 100. Okay, is this okay to everyone? Yes, silly mistakes might happen, but that's fine. Okay, that's fine. So can you tell me what is the answer? See, this was a MSQ question, by the way. So they are asking distance to 1. Is this 80? Yes, this is 80. Distance to 2. Distance to 2. Where is 2? 2 is this. Is this 110? No. It is actually 100, right? So it actually got updated. So that's why this is wrong. Distance to 3. Distance to 3 is 70. Yes, that's correct. Distance to 4 is 30. Yes, that's also correct. So basically, you can see A, C, D are the correct answers. Okay. So it was easy question, and A, C, D are the correct answers. So A, C, D are the correct answers here. So in the Bellman Ford, by the way, what we do, we can relax in any order. Okay. Remember, we can relax in any order, but they have given that we have to follow. Okay. So in the question they are saying, within a single pass of algorithm, the edges are relaxed strictly in following order. Okay. They are saying you are following strictly this order. Right. Great. Now let's see this question. In this question, they are saying that every fifth transmission is lost. Okay, every fifth transmission is lost. So you can see, maybe I can do a fresh, take a fresh page. See here, they are saying in go back, and they are saying every fifth transmission is lost. So 4, 5, and the size of the window is also given to be 3. Okay, so this is lost basically. This is lost, right? And at this time you have already transmitted 6, 7, because size of the window is 3. So that's why since this is lost, you have to transmit 5, 6, 7 again, right? You have to transmit this again. But now what is the fifth packet? Okay, what is the fifth packet? Tell me in the retransmission. I mean, if this is lost, then what is the fifth packet? One, 2, 3, 4, 5. The 7 will be the next fifth packet. See here, the 7 will be the next fifth packet. So this 7 will be lost again. Is this fine to everyone? See, from this lost, what is the fifth packet? 7 will be the fifth packet. So it will be lost again. So when it is getting lost, actually you have already transmitted 8, 9, right? Okay. And you have to transmit how many packets? Total 10. So we already transmitted 8, 9. So you will be again going to retransmit 7, 8, 9. And then you will see that the fifth packet, 1, 2, 3, 4, 5, this 9 will get again lost, right? And at that point in time, you have already transmitted 10. So you are now going to retransmit 9 and 10 also. Okay. and then every fifth is lost, so now there is no fifth. I mean, there are only three packets you have transferred, so basically it will get successfully delivered. So you can check, these are the 5, 6, 7, 7 packets, 10 packets from till now, 10, and then 1, 2, 3, 4, 5, 6, 7, 8. Okay, so total 18 packets you have to transfer, 18 packets, right? So it was easy question only, right? It was easy question only. Now let's move to the so it was easy question basically. Now let's move to the next question. So you might have seen the solution. I've actually written the detailed solution. Okay, and if you have seen, I've written the detailed solution already. Again, this was again related to go back n, and here this is saying that if you are transmitting, okay, here the window size is again 3. This is saying that if you are transmitting the packet, during the transmission, packet number 1, okay, the packet numbering start from 0, and then they are saying packet number 1 and packet number 4 are lost. So basically you transfer 0, okay, 1 and 2, and then obviously you will be transferring 3, right? You will be transferring 3. So let me write in the horizontal way. So basically 0 you have transferred, 1 you have transferred, 3, 2 you have transferred, 3 you have transferred. And they are saying that packet number 1 actually lost. Okay, if this is lost, then probably you might have retransmitted 1, 2, 3 again, which is fine. Okay. And packet number 4 is also lost. So now this is also lost. If this is lost, then after that maybe 5, 6 might be there. Okay. So you have to retransfer the whole window because window size is 3. Now, what they are saying, A must retransmit the A must retransmit the required set of packets. So basically, once this is lost, this is the second timeout, right? So they are saying that which of the packet A retransmit after the second timeout. So this is the second timeout, and once this timeout is over, you have to retransmit 4, 5, 6 again. Okay, so you have to retransmit 4, 5, 6. So that's why C is the correct answer. That was easy question. I mean, that was also not hard question. I think this was easy question. It was expected that you should be doing this question, right? Okay. See, in GATE also they ask these easy questions. It's not like that GATE will only ask the tough questions. Okay. In GATE also they are going to ask easy questions, and you should be able to do easy questions if you have already done that topic. If you have not done that topic, it's a different issue. But if you have done the topic, then these questions are approachable. Okay. Now let's see this question. In this question, basically we are testing something related to banker's algorithm. So they are saying that total 10 instances of some resources given. Okay. And then this is the current state of the processes, which means P1 already has one resource, P2 already has one resource, P3 has two resources, and P4 has four resources. And maximum at maximum they might need in future. Okay, this is the definition of the maximum, that they have to tell the maximum for the banker's algorithm. Okay, so in future they might need, okay, at most, I mean at the maximum they will be needing 6. So one is already allocated. So you can say 5 more will be needed. Okay, so this is the definition of maximum. I think most of you already know this definition. Okay, what does this maximum mean? Now they are saying if one additional request is made, which of the following statement about the system safety is or are correct? So one, if someone is requesting one more additional request, right? Then which of the following is or are correct? If P4 does that request, then system is in safe state. Or P3 does that request, then system is safe or unsafe. That's what they're asking. Okay. But before I go to the solution, let me tell you that some of the students got confused that what does this mean? Okay, one more request is made. See, this is the deadlock question, and here we are going to apply Banker's algorithm, right? Banker's algorithm is something that is, we are going to apply here. You might already know this. Now, now you see one thing here, that Banker's algorithm we apply to check whether this current system is in safe state or not. Okay, they are not asking for the current system whether it is safe, it is in safe state or not. Basically, we apply Banker's algorithm for the dynamic checking also, which means suppose P4 is requesting something, some resource, then should be allocated or not. So how do we do it? We assume, okay, I mean we don't actually do it, we assume in case if we do it, okay, then we calculate the numbers like allocated, maximum, and these things, and need, and these things, then we see if there exists a safe sequence or not. So basically some of the students got confused that whenever I'm saying if one more additional request is made, okay, they got confused with this line, and then they are thinking that maybe we should be having +1 in the maximum or something like this. Okay, let me just tell you probably. Yeah. So basically, uh, someone is if someone is interpreting the statement like if p4 requests one more instance, see here I'm saying in the option a, if p4 requests one more instance, the system stays in safe state. See, if someone is interpreting the statement like if P4 requests one more instance as an increase of maximum demand, that interpretation is incorrect. Okay. It's not like that they are asking for the maximum. See, it's not like P4 will be from here 7 to 8. See, maximum is always fixed. Okay, fixed. No one can change it. No one can literally change it because that has to be fixed while you are submitting the process. Okay. In banker's algorithm, the maximum requirement of the process is fixed beforehand at the time process is submitted to the system, and it never changes during the execution. This question is basically just asking you to apply the standard banker's algorithm. One of its primary purpose to is to dynamically check whether the resource request can be safely granted or not. Okay, so here we will be just checking what if we give one more resource to p4, then will the system will be in the safe state or not. Okay, this is that simple. I don't know like why people got confused. Okay, in fact gate has asked such dynamic checking questions. I mean, if you see this gate 2009 question, gate 2014 question, they've even asked these type of questions where they are not just asking, okay, apart from the question, we are just asking the static snapshot of the system whether it is safe or unsafe. I mean, one of the see there are two type of question. One type of question is that given the system, check if it is safe or unsafe. Okay, this is one type of question. Second type of question is that given the system, I'm not asking whether it is safe or unsafe. Like let's just assume that they have already calculated it is in the safe state. Given the system, okay, if some other resource, okay, have some more request. Let's suppose p4 is requesting some other instances or something like that, then after granting, will the system will be in the safe state or not? Have you understood that what does this two type of question mean? One is that given this state, whether it is safe or unsafe. This is one type of question. Another is that given this state, I'm just asking you if some other process is doing some more request, then after granting, will it be in the safe or unsafe? Okay, so let's just check whether after granting this request, whether this system will be in the safe or unsafe state. So let me do one thing. Let me just copy this to the next page. So actually, many of the students got confused. Many students, okay, that what does this mean? But it is a standard terminology. I mean, in fact, I've taken this question from some university. Maybe I have given. Okay, in under this question, I've given the link. You can see under this question, I've given the link. You can see that link, but but you can easily expect you can easily expect exactly same wording in gate. I mean, there is nothing wrong with the wording. Such questions are 100% correct and valid, and many universities as well as the standard textbook uses this terminology. Okay, so many people use this terminology, so don't worry about this terminology. It is 100% correct, right? One more request means that p4 is requesting something. That's the normal interpretation. I don't know how students got it wrong. Maybe this is the first time they are seeing this kind of question. Maybe, okay, maybe that is the reason. Otherwise, this is perfectly valid. In fact, from the source I have taken this question. At that source, okay, the link I have already mentioned in the under this question, maybe in the answer or in the comment. But what I'm saying here is that uh, see, in that particular resource from where I have taken this question, they have used exact same wording. I have not even changed the comma. Okay, they have used the exact same wording. If p4 request one more instance, exact same statement they have also used. Okay, okay. So let's just do this. See, currently how many are already allocated? 8 are already allocated, right? So allocated total are 8, and how many are available? Available are basically 10 minus 8, which is 2 resources are available. Okay, if p4 do one more instance request, then what will happen? That allocated will be 5. Okay, for p4 allocated will be 5. Now let me also calculate the need first. I hope you know how to calculate need, right? It is just the maximum minus allocated, so its need will be 5. Let me do some division. Okay, so this will be 5. Mm, yeah, this will be 5, this will be 4, right? This will be 2, and this will be 3. Okay, this will be the need. Now suppose I ask this P4 that, okay, let's just, I mean, I'm not actually granting, which means banker's algorithm doesn't actually grant it, just check. Suppose you say that, okay, one more resource is allocated, so the need will be 2, right? The remaining need will be 2. Is this okay to everyone? If one more resource is getting allocated, then remaining need will be 2, right? So available will be basically 1, because one more resource has been allocated. So now this is the current state. Basically the allocated, you can say, it is 5. Okay. Now this is the current state. Now see, if available is 1, and these are the needs, can you fulfill at least one process need? No, right? Okay, so one of the student has commented that actually the teacher from where from whom I studied. Let me just do one thing. Maybe, yeah, let me just show this comment. So basically, one of the student just commented this, that actually the teacher from whom I studied, he taught us that one more instance requested means added to the maximum, which means increase the need column. Increase the why? Okay. Oh no, man. Okay, this is hilariously wrong. Okay, this is too much wrong, I think. I don't know the context in which the teacher has told you, but if the context is same, then this is too much wrong. Okay, so this is wrong. I mean, one more instance means that you are requesting, right? You are requesting, which means if you're granting, then allocated will be increased and need will be decreased. Okay, need column will be decreased, not increased. Why will need be increasing? If you're requesting one more. Oh, one more. P4 is requesting one. See, maximum is fixed. If P4 is requesting one more, then and then let's just assume it is allocated. Okay, that's how the banker's algorithm really work. I mean, there is no point in increasing the maximum. Banker's algorithm work in exactly same way, that you have some system. Okay, the snapshot sort of system. So suppose you have this system. This is the current system. You can say, right? This is the current system that you have with you. Okay, and then if some process at this system, okay, this is the system that you have, which is, suppose initially it is in a safe state, right? Now how does the banker's algorithm work? If someone requests something, if some process requests something, then what do you do? If some process requires something, then what do? Then you do one thing. You just pretend, I mean, the banker's algorithm pretend that that particular resource has been granted, and check whether it is in a safe state or not. So banker's algorithm pretend pretend that resource is granted, and then check if system is in safe state or not, right? Safe state. Have you understood now? Okay, it will just pretend, right? So basically, if someone is requesting something, I mean, that's how the bankers algorithm work. If someone is requesting something, it will just pretend, let's just allocate it, and then let's just check whether now the system is in safe state or not, right? So let's just check it. If you just allocate it, then the available will be 1, and you cannot fill anyone's need, right? See, you should be understanding what does this need mean. I think I should be creating more such question. Maybe you people are not very much. I think, I mean, you people are just used to of applying the banker's algorithm, but do not really have the feel of this banker's algorithm. See, do you really understand what does this need mean? Need means this is the maximum. I mean, future need, right? This is the maximum future need. Tell me, given this instance, can P1 request just for 2 instances? Okay. At the next time, can P1 request just for 2 instances? Tell me. Obviously, yes, right? Future need is 5, so it can request less than equal to 5. Okay, it need not to be necessarily request for 5 instances at the same time. Okay, see, if you see these gate questions, the link you will be finding under this question. So if you see these questions, they actually specified that, like for example, at t equal to 0, p1 is requesting 4 instances like this, right? I mean, they've even given the times that at t equal to 0 this is happening, like that. So basically need means that it is the maximum need in future, that the resource will that the process might be needing. Okay. So basically, currently, we say that okay, available is one. Then in that case, that what if, okay, so we have to be in the safe state, which means that what if P4 request, or any other process in future request the maximum, which means two directly. If any other process request one, then probably we will be able to fulfill, right? But what if they request with the maximum need directly? Then it will be in the unsafe state. So basically, it is unsafe state, right? Unsafe, because an unsafe state doesn't mean deadlock. It all depends on the future needs. Okay, in future may not be needing two. Okay, maybe it is just needing one, right? Okay. Anyway, let's just do one thing. I will be creating one very creative and very nice question related to this meaning of need and maximum and all, for the next AIMT. Okay, just mark my word. In next AIMT, one question which is going to be AIMT 2, one question related to the meaning of these. Okay, meaning of need, maximum, these things. It will be a theoretical question, but I will make sure that this question is going to be a very nice question. Okay. Yeah. So basically, we have just seen that if P4 request one more instance, then in that case, system might go to unsafe state, right? If P4 request one more instance, then the system might go to unsafe. Yes, this B is correct. What about P3? Let's just check P3. So if P3 request one more, which means the need will be one. You have to decrease the need, not increase. Okay. In that case, need will be one, right? And the allocated, basically, you can say it will be three. So allocated will be three. Okay. So allocated will get increases, and the available will be basically one. Okay. Available is now one. Okay. So now tell me, in that case, can you fulfill at least one process request? Yes, you can fulfill P3, right? So P3 you can fulfill, and once P3 is fulfilled, so allocated is three. So basically, you will be getting four. Okay, I mean total available will be four. Now with this four, can you fulfill at least one? I think you can fulfill P4, or you can fulfill P2. Okay, let's just do any one of that. Let's just fulfill P4. Okay, if you fulfill P4, then allocated as 4, so basically 8 are now new available are 8. Okay, with 8 I think you can even fulfill you can fulfill anything, right? You can fulfill this or this, and then you will be getting some sequence, maybe P1 or P2, doesn't matter, right? So basically this is the safe state. Okay, this is the safe state. Now, so basically, you can say that with P3, the system is in the safe state. So there are multiple safe sequences. I mean, this is the safe sequence basically. So there are multiple safe sequences. So basically, you can say B and D are the correct answers. Okay. See, students are commenting here. I think one more students have commented that, sir, one more instance request means P4 need will increase by one. No, I don't know who is teaching you this. This is the new misconception that I just got to know. Okay, this is literally a very bad misconception. So I think this is going to be. I mean, your new question which I'm going to give in the AIMT. I think this question is going to be very much fun, because I will make sure this is very good question. So this is actually a wrong concept, and you are, you know, just having a misconception. If some process is requesting, it means you are allocating. I mean, banker's algorithm pretend to allocate and then it does the job. Okay. So basically, banker's algorithm pretend that, okay, let's just allocate and then just see that whether the system is now in a safe state or not. Okay. That's how the banker's algorithms work. Okay. Now let's just move to the next question. So let's see this question. In this question, they are asking mutual exclusion, progress, bounded waiting, these things. Okay. So let's just see. Okay. Tell me the mutual exclusion satisfied. See, can you enter into the critical, can both the process enter into the critical section at the same time? Let's just see this. Can both the process enter into the critical section at the same time? See, whenever they try to enter, okay, then they will make their own flag to be true. The moment their own flag to be true, okay, and this is also true, then basically they cannot, I mean, both cannot enter, right? I mean, if both are trying to enter basically at the same time, obviously they can't enter. Okay, because then it will be a deadlock. If they enter one by one, either they will be entering at the same time or they will be entering one by one. That's the only two possibilities. I mean, there should not be any confusion. At the same time, obviously they can't enter. What if they enter one by one, which means, let's suppose I ask first process to get enter. Okay, now if this is in the critical section, then in that case, can this enter? Let's just check. Flag one is true, that's fine, but it will get stuck in this loop, right? So both process cannot be at the same time, they cannot be in the critical section. So you can say mutual exclusion is satisfied, right? Mutual exclusion is satisfied. Understood? What about the progress? See, progress says that there should not be any deadlock, right? So basically, if you just ask it to enter, I mean, if you just have one case where both the processes are entering at the same time, then they might get involved into the deadlock, right? So there is a deadlock. Deadlock is there, it means there is no progress, right? Is this understood, everyone? Okay. Now the third is bounded waiting. Bounded waiting means, to check the bounded waiting, there is a fixed method. The method is that you ask one of the process to be here and you ask another process to be here. Okay, I'm just checking bounded waiting. So which means, let's just suppose that one of the processes is in this loop. Okay, see, the second process is important. Don't assume that second process is here. I mean, here means that no, not related to critical section, it is somewhere here. It has to stuck. I mean, see, if one process, let's suppose p0 is here, then assume at the same time. Okay, this is the initial condition of bounded waiting. I hope you might remember. Just assume that at the same time that p1 is here. I mean, it is definitely possible that p0 is, if p0 is here, then if p1 try to execute, then it will be in the it will be in this loop, right? Okay. Now just check, can p0 go out and come again? Okay. I mean, I'm not scheduling p1 currently. Just check if p0 can go out and come again. See, if it go out, then flag 0 is false, flag 0 is true, that's fine. Then can it come again into the critical section? No. Why? Because flag 1 equal to true, it will get stuck here. Get stuck here, right? Because flag 1 is already true. So that's why bounded waiting is also satisfied. Why? Because p0 cannot go out and come again. Understood? So bounded waiting is also satisfied. See, mutual exclusion satisfied, progress is not satisfied, but bounded waiting is satisfied. Why? Because you just ask, I have written the same explanation. Basically, you just ask whether p0 can go out and come again. If that can come again, it means there is no bound that p0 can enter how many times, right? There is no bound on that. So that's why bounded waiting is not satisfied in that case. But here p0 cannot come again, so that's why bounded waiting is satisfied. Okay. Yeah, let's see this question. In this question, I'm just asking, suppose there is a queue, okay, which is having uh front to rear. Okay, so basically it is 1 2 3 4. This is a queue, right? Now there is a stack which is initially empty. What I want to basically, you must transfer all the elements from Q to S. such that the front element of q becomes the top, which basically I want this something like this, right? 1 2 3 4. The front element I want to be on the top. Okay. Basically, I first want to insert 4, then 3, then 2, and then 1. So how many minimum number of push operations will be needed? Yes, answer is 4, right? So how to do it? See here, this is 1 2 3 4. You want to insert such that this 4 should be inserted first. Okay, first you want to insert 4, and then 3, then 2, and then 1, right? See, if you want minimum number of operations such that you can insert 4 or something like that, then then what you do, you just ask repeatedly a minimum number of push operations. Okay, you just ask repeatedly to go into this particular queue. I mean, just pop it and push it, or pop it, push it, or NQ DQ, such that 4 is at the bottom. Okay, I mean, can you not do something like this from this queue? Can you not go to something like this? 4 is at the bottom, and everything else is here. Can you not do something like this? Everything else is here. We can do it, right? So how? You can just pop this one. Okay, and then you can do something like this. You can just NQ DQ this. I mean, you can just pop this and push it at the end. Or if you are not using pop and push, you can just use NQ and DQ. But the pop and push, I'm just using as an English, not as a technical term. So you can pop it and then you can push it, and then you can do the same thing for 2. Okay, I mean, you can just do the same thing for 2. So 3 will be at the end. 3 4 1 2, and then you can do same thing for 3 also. So basically you can easily achieve this, and then you can pop it, and then you can pop it, and then you can directly go to 1 2 3. I mean, now you don't have to push it, you can push it here. So basically there will be just one push for the stack. For 4 there will be one push. Similarly for 3 also, you just do the same rotation. I mean, you just make sure that 3 is at the front, and everything else is here. You can definitely make sure. Once this is make sure, then put it here, right? So minimum number of push is basically for every element you will be just needing one push. So four pushes will be needed, right? Okay, great. So answer is 4. Now let's just see the next question. So in this question, they are asking that some keys are given. Okay, and then this is 11k plus 4 mod 9 is there. I mean, some hash function is given. Then they're asking that if you're using the chaining, then which of the following options are correct? Okay, so what you can do, you can just apply this 11k plus 4. So if you do it for 67, so 67 into 11 plus 4 mod 9, right? So I think if it is mod 9 already, then what is the point of writing 11? Can you not write 2? I mean, it's same as 2k, right? I mean, ultimately the remainder is 2. So it is 2k plus 4. Either you do 11k plus 4, or you do 2k plus 4 mod 9. Both will be the same, right? So you can do 2k plus 4, doesn't matter. So let's just do it. So this will be 2 into 67. 2 into 67, which is basically 7 दूनी 14, 1 and 7 12 13 plus 4 138, right? 138 divided by 9. So let's just do it. 138 divided by 9, it is 15 point something. Just a second. So it is 11 into 67 plus 4. Okay, this is mod operation, sorry, mod 9. So how much you are getting? I think we will be getting 3, right? Okay, we will be getting 3. So if you do the mod 9, then it is a 3. So basically in the bucket 3, you will be having 67. Okay, so I think I have the answer. In the bucket 3, you will be having 67. And then 13 will be in the bucket 3. So you just have to apply this hashing function. By the way, this question I have taken from MIT. I mean, this is easy question, but still I'm just telling you, I have taken this from MIT. Okay, great. Now let's just do the next question. So in this question, actually, most of the students got confused. What does the size mean? Size of the largest maximum binary heap that is also a valid binary search tree. So they got confused with this word size. Let me just tell you that size of a tree is a valid and fixed definition. See, see, if you see, uh, if you see Wikipedia also, let me just tell you. If you see Wikipedia, I have taken this screenshot from Wikipedia. Okay, and in this screenshot, you can clearly see that size 9, and then in the bracket, they're writing the number of nodes in a tree. Basically, size of tree is fixed. I mean, this is the well-defined definition where size means the size of a tree is defined as number of nodes. Okay. I mean, this is fixed. There is no confusion here. It is just one definition I wanted to use. And in fact, Gate has already used this definition. Let me just tell you. In Gate 1998, they've asked this kind of question that drive the recurrence relation for the size of the smallest AVL tree. Okay, I mean size of the tree, right? Size of the tree. Size of the tree means number of nodes. Gate has also used the size definition, number of nodes. It's not that we are only using. In fact, Gate might not have used. It doesn't matter. Basically, the size is a well-defined term in case of tree, right? So size it basically means we are interested in finding the number of nodes. So basically they are saying that what is the size of largest maximum heap, which means that I'm just asking the maximum number of nodes in the heap such that it is binary search tree also. So the question can be written as maximum number of nodes in heap such that it is binary search tree also, right? Okay. So see here that the term size of a tree is well-defined term without any ambiguity. Also, actually, one of the students shared this Gate 1998 question, so I just said that okay, thank you. Even if Gate had not used this terminology earlier, the question is still perfectly valid. Okay. In fact, I've taken this question from this source. So on that source also, if you see on that source also, they are just saying that what is the size of the largest maximum heap that is also a binary search tree. I've taken this question from here. Okay. So basically, I'm just asking the maximum number of nodes that heap can have. So you can say that suppose there is some number 10. Since it is a maximum heap, so it should be the maximum number, right? And below it should be the below. I mean, below it should be the lower number. But in the binary search tree, it says that on left it is lower. Let's suppose 5. In the right, it should be greater than 10, right? Greater than 10. But in the heap, it is not allowed. So basically, this is the maximum size that a heap and binary that can be heap and binary search tree both. Okay. So the answer is 2. Because in the binary search tree, it says greater than 10, but in heap, it doesn't say greater than 10. So that's why this is the maximum size. Okay. So 2 is the correct answer here. Now let's see this question. This was a simple C programming question. So in this question, they are saying that let's suppose, let me just zoom it a little bit. So they are saying, let's suppose there is a function alpha in which I'm passing the address of 5 and 7. Okay, so L plus equal to, R. So basically they are saying that now X value, since I'm passing the address, so star L and star R will do the same thing that, I mean, they will reflect the value. So basically it is basically saying that now a- L means X, right? So X equal to it is like X plus Y. So which means X value will be now updated. This is why initially there are 5 and 7. Now X value will be updated to 12. Okay, 12. Now Z is something that they are returning. Okay. Uh, R is some local variable, right? I mean, R is some local variable, local pointer, you can say. Okay, so R is here, which is a local pointer. And R is actually pointing to Y, right? R is pointing to Y. Now, star Z means star R plus equal to 3, which means you are modifying this to 10. Okay. So 12 10 will be the answer. 12 10 will be the answer. So basically B is the correct answer. It was a good question in the sense that we are returning, R, which was a local pointer, but it is still pointing to Y. Okay, it is still pointing to Y. So that's why this question is basically little bit interesting. That's the reason I have put this question. So B is the correct answer. Okay. Okay, someone is saying that please explain again. See, initially X and Y are 5 and 7, right? So this is X, which is 5. This is Y, which is 7. Now you're passing to some function and L and R start pointing here, right? L is basically pointing to X and R start pointing to Y. Okay. Now star L plus equal to star R means like this will get modified to 5 plus 7, okay, which is 12. Okay, this will get modified to 12. Now they're returning R, which is fine, and R value is taken into Z. So basically now there is some other variable which is Z. It is also pointing to Y because it is same as R. Okay. Now star Z plus equal to 3, which means now this value get modified to 10. So final answer are 12 and 10. Okay. Final answer are 12 and 10. So which means B is the correct answer. Okay. Now let's solve this question. In this question, I have taken the 2D array, okay, which is like 3, 5, 7, 2, 4, 6, 8, 9, 10. Okay. Some 2D array I have taken. And then I'm saying that this is basically star A. See, the A is a pointer to 2D array, but star A will be the pointer to the 1D array. Okay. Star A will be basically pointing here. And then A0 equal to 3, this is true. So that's why it is actually just 1. Okay. This is just 1. So basically star A plus 1. This is same as saying star A plus 1. Just take care of the brackets, I think. This is one is okay. This is the bracket and yeah. Okay. So yes. So basically they are saying star A plus 1. Okay. So it is same as saying this. Now star A means this. Star A plus 1 will be actually this. Okay. And then the moment you put one more star, it will be 2. So the answer is 2. Just a second. Okay. So basically this is A00 equal 3. A003, this is true. So it is star A plus 1. Yeah, okay. So sorry, this is actually A01, which is same as 5. So sorry about it. So basically, star A plus 1 means like A is pointing to the whole array. Star A will be pointing here. So star A plus 1 means star A plus 0 is this. Star A plus 1 will be this. Okay. So star A plus 1 will be pointing here. And the moment you put one more star, it will be basically saying that now you are talking about the 5. Okay. Now you are talking about the 5. Yes, you are correct. So yes, star A is basically pointing to 3 and star A plus 1 will be pointing to 5. Okay. So A is actually pointing to this row. Okay. So see in 2D array, this is 3, 5, 7, 2, 4, 6, 8, 9, 10, right? So in 2D array, A points to the first row. See, in 1D array, if you remember, in 1D array, A points to the first element, right? A points to this. Similarly, in 2D array, A points to this, the first row. Okay. And star A will point to 3. So basically, you can say, let me just visualize it, that A points to this and star A is going to point to this 3. The moment you put a star, it is only going to point to 3. Okay. And star a plus 1 will be pointing to 5, and star a plus 1 will be pointing to 5. And then you can see that the moment you put one more star, it is basically saying this is star, okay, plus 1. It is basically saying 5. Okay. So star is pointing here, star a plus 1 will point here. Or otherwise, if you are getting confused, star a plus 1 plus a star basically, for that you can just write it like a01. Okay. And then you can see that 5 is the answer. Okay. So yes, that could be a silly mistake. Basically, A doesn't point to the whole array. A points to the first element. Okay, A always points to the first element. That has to be necessary. Otherwise, A plus one is actually wrong, right? I mean, so A doesn't point to the whole array. It points to the first element. So star A will be pointing to 3, and star A plus 1 will be basically pointing to 5, and then whole star of this will be actually 5 only. Okay. Now let's see this question. This was actually very very easy question. Here, let me just zoom it out. Here we are saying x is not equal to 0. Okay. Actually, x is equal to 0, so this is false, right? This is false. The moment it is false, you will not execute this the next statement because of the end. Okay. So you will not execute this next statement. You will just say that, okay, let me just skip this whole if condition and let me just go here. So initial values are 0 and 5. So 0 and 5 will be the answer. Right. So is the answer. Why? Because this will not get executed. Not get executed. Okay. So you will directly say 0 and 5 are the answers. Yeah. Now let's just see this question. This question was very nice question, but some of you have gotten it wrong, and most of you, were not taking in the way in like most of you were not basically taking in the same way that we have intended to solve it. So basically, in this question, I was asking you the rank of A, where A is some matrix which is basically something like this. I mean, which is because of a vector x. Okay, these are the column vectors, vector x and then y. I mean y transpose. So basically, it will look like this. So it will be a matrix. Now they're asking the rank of this matrix if these are the non-zero. Do you remember one property? Do you remember the eigenvalues of AB and BA? What is the relationship between the eigenvalues of AB and BA? So non-zero eigenvalues are same, right? You might remember eigenvalue of AB are same as non-zero at least of our BA, right? Eigenvalues of BA. Do you remember this? So non-zero eigenvalues are same. So instead of doing like this, let me do in other way. So instead of let's just treat this as A and let's just treat it at B. Okay. Let me do in other way. Let's just do BA. So it will be B, which is Y transpose, and A will be something like this, right? This is X. So this will be a scalar number, right? This will be a single number, isn't it? This will be a single number. And what is the eigenvalue of the single number? Can you tell me? What is the eigenvalue? The number itself, right? I mean, the number is within the bracket, so it is just a single number, or you can treat it as a singular one by one matrix, right? So you can see that if I just ask you what is the eigenvalue of this, you know, uh, sorry, this vector, this. Suppose you can treat it as like a matrix multiplication, and then you can ask the eigenvalue of this. Can you tell me the eigenvalue of this? This will be the final. It will be a scalar, right? A scalar, and the same eigenvalue will be there. So the same thing, right? This is the eigenvalue, isn't it? So the same eigenvalue will be here. Now, if I ask you instead of this multiplication, okay, this is let's suppose y transpose, this is x. Instead of this multiplication, I ask you to have this multiplication. Then eigenvalues will be at least same. right? So this will be having the same eigenvalue as this, isn't it? The eigenvalue of this, let me write, eigenvalue of this will be same as the eigenvalue of this, because a, b and b has the same eigenvalues. Actually non-zero eigenvalues will be same, and this eigenvalue is just a scalar, right? Okay, so there is just one non-zero eigenvalue, you can say. Okay, for this matrix, there is just one non-zero eigenvalue, right? Okay. Or if you see, if you are not very much familiar about the eigenvalues and all, you can also do with the matrix multiplication, which is also fine. Which means, see, let's suppose this y transpose is 1 2 3. Okay, let me just tell you one other way. Suppose this y transpose is 1 2 3. Can you tell me how will the matrix multiplication look like? If you remember, it is the basically linear combination of these columns. Since it is just one x, so the first will be x into 1, or 1 into x. The second column will be 2 into x. The third column will be 3 into x, isn't it? So you can say it will be having the linearly dependent rows. So that's why rank will be. So what I'm asking here, yeah. So then the rank of A, it will not be n basically. It will not be n. I mean, it will be dependent on a. It won't be any fixed quantity. Okay, at least n by 2 or something. I cannot say. So what will the rank, by the way? Only one linearly independent row. So you can say, or with linear independent column. So rank will be 1. Okay, so rank will be 1. I mean, if you do this kind of multiplication, then you will be getting rank will be 1. And from here also, you can see that only one non-zero eigenvalue is there, and this will be basically, I mean, this is kind of, I'm not going to much detail, but this is kind of diagonalizable matrix. Okay, in that case, number of non-zero eigenvalue will be the same as rank. So here also rank will be 1. Okay, but I think this might be the easier way for you. So you can see that if you're multiplying these two things, I think in gate also, in gate 2021. Okay, in gate 2021 they've asked similar kind of question, almost similar kind of question. So if you do some, this is called outer product. Okay, this is called outer product of vectors which result into the matrix. If you do this outer product of the vectors, then you will be getting only one linearly independent column. Okay, so rank will be finally 1. Okay, now let's just move to the next question. Let's see this question. In this question, they are saying you have even parity, right? So even parity bit may be appended to the bit stream. A serial receiver that uses the even parity has received the following 9 bits, parity bit followed by 8 data bits. So basically, you have one parity bit, so 0, and 8 data bits, which are 0011 and 0100, right? So these are this is the data that you have received. And what does this even parity mean? Even parity means that including the parity bit, total number of ones should be even. So currently total number of ones are odd, right? So there must be some error. Error may be here from 1 to 0, like maybe they have flipped this, maybe from some 0, okay, that has got converted to 1. So basically maybe 1 to 0, maybe this 0 to 1, right? Okay, or maybe there could be multiple at multiple places there could be the error, which means probably some 1 got converted to 0 and some 0 got converted to 1, which means initially it might be like this is 1 and this is, yeah, this is 0. Yeah, this one might got converted to 0, or maybe there are multiple possibilities. Let's just see with the options. So one of the option is saying no errors. No, this is not true. Obviously there has to be error, right? There has to be error. Second option is saying there is even number of errors. Third option is saying there are odd number of errors. So let's just go to the next page and let's just try to understand this question. This is 0 0 0 1 1 and 0 1 0 0, right? So we are using even parity. Can there be the even number of errors? So can there be the even number of errors? Which means, is it possible that two bits has got flipped, or maybe 4 bits has got flipped, or something like this? Just think about it. See, suppose there are even number of errors, which means initially, let's suppose these are 1 1, now they got converted to 0 0. Okay, suppose there are even number of errors. In case of even number of errors, the number of ones, see, number of ones will be basically, if both are the one, earlier if both are the one, if they got converted to 0 0, then it is not possible. Why? See, the one of the one, actually I have to take from this. See, the thing here is that currently there are odd number of ones, right? Odd number of ones. So if you are having even number of errors, it must mean that you must be having basically, see, it is possible that you might have converted